Good evening and welcome to Monday Night Calculus with Steve Kokoska and Tom Dick. My name is Curtis Brown, and I'm super excited that you guys have chosen this evening to join us here. We're going to be working a little bit of calculus. Steve and Tom have prepared both some problem sets for you. I know some of you guys have already asked for those on the chat, and we'll be getting a link to you shortly where you can download those. But yeah, we're going to be looking at a few problem sets, and Tom's got some technology tips for us and things going that way. But I just wanted to point out a couple of things. We're going to be doing this for quite a while now. We're going to be doing it the next couple of months. We'll be doing it every Monday night, every other Monday night, so every 2 weeks. And we will have new problem sets each time. Steve and Tom are going to be putting those together, and we will be posting them. I believe the chat should have the link now. If it doesn't, I'll put it up there real quick. Have the link to a bulletin board post where those problem sets will be posted every week. So you guys can check those out. The solutions will be there as well. So we don't have them up there for this week's already. We will post those this coming Friday. And then we'll just continue that sort of process. We'll do the session on Monday night and then post the solutions on Friday afterwards. But this would be a really great time to try to get used to the ideas and what we're going to be sharing. So tonight our topics are infinite limits and limits at infinity. So Steve and Tom, will you guys take it away?
Thank you very much, Curtis. I'm going to share my screen here and bring this up if I can. And let's see. How's that? Okay.
Looks good.
All right, I'm going to make that a little bit bigger, and here we go. How's that? Well, thank you very much, Curtis. I'm sorry I have to say this. Are you ready for some calculus?
All my rowdy friends are here on Monday night. We're ready.
All right.
Let's do it.
Very good. Thank you very much for putting this together, Curtis. Tom, it's a delight to work with you as always, and Allison, thanks for the technical expertise. What we're going to try to do tonight is give a little brief content presentation, some background information also. I'm going to work a couple of examples. Tom eventually will introduce some technology. I'm going to discuss our 914 questions or exercises that we posted on the bulletin board. And of course, we'll take questions along the way. Anytime you have a question, if you put it in the chat window, somehow it'll get from Allison to Curtis to one of us. So tonight we're going to talk about limits at infinity and infinite limits. A little bit different topic for Tom and I. We haven't talked about this before, and we thought that this would be about the place where many of you are in your syllabus. So let's take a look at this. The first thing I want to do is take a look at a special case in which a limit does not exist. So let's consider this function 1 divided by x minus 2 quantity squared. And let's take a look at the limit as x goes to 2. Now, one of the things that my students always want to do, of course, is to simply plug in that value of x. And if they do that, of course, the numerator here is still constant and going to 1. And the denominator, of course, is 0. You'll notice that I did not write 1 over 0 equals 1 over 0. So right now, that's not a good thing in AP Calculus. But the numerator is going to 1, the denominator is going to 0, and I don't know whether or not this limit exists. So this being AP Calculus, let's investigate this numerically and graphically. So on the bottom left-hand side, I've created a table of values. And in this left-hand column, these are values of x as x approaches 2, if I've got this correct, from the left-hand side. And these are values of x as x approaches 2 from the right-hand side. So you can certainly tell better than I can that there's a lot of symmetry in this function, and I've indicated the function values in that third column. And boy, it certainly looks like the value of this function is increasing without bound as x gets closer and closer to 2 from both sides. And on the right-hand side, I have a graph to sort of support that. You know, we always take a look at things graphically, numerically, if we can in AP Calculus. And it certainly looks like that. As I get closer and closer to 2 from the right and from the left, the value of the function is increasing here without bound. So let me talk just a little bit more about this, and that will lead us into a definition, I hope, eventually. Here are a couple of my observations. It certainly appears to me that as x approaches 2, x minus 2 squared approaches 0. And I'm going to step aside just for a minute here. And I'm going to describe this behavior in this particular denominator like this. This is sort of my own notation. I'm not saying that this is AP calculus notation. But if an expression is approaching 0 through small positive values, that's the kind of notation that I like to use. That helps me analytically determine a limit later on. And I'm going to use some of that notation. So if x minus 2 squared is approaching 0, this denominator is getting smaller and smaller positive, and that's forcing the whole fraction to become large. So both the table and the graph suggest that the values of f can be made arbitrarily large by taking x close enough to 2. So in the traditional sense, that certainly means that f does not approach any specific number, and therefore that means that this limit does not exist. However, this kind of behavior we write in a special way. So I'm going to take what I call a closer look at all of this. I'm going to dive a little bit deeper into these ideas, these concepts, and try to explain it in layman's terms so that I can understand it. So this unbounded nature of this particular function, we usually write like this. The limit as x goes to 2 of 1 divided by x minus 2 squared is equal to infinity. And maybe I should stop there for a second. Some people are very uncomfortable by writing equal infinity because, of course, infinity is not a number. But we as mathematicians understand this notation. We know that infinity is not a number, and we understand that this particular notation describes a very special kind of behavior of this function near 2. It describes the behavior of this function near 2. We just have to remember that infinity is a symbol and not a number. So even though we use an equal sign, the limit does not exist, but this particular limit has this special kind of behavior.
Hey, Steve.
Yes?
I've got a question that just came in from the chat. I just want to let you know, first of all, that we've got just a slight delay between the chat and what you're presenting, so just a heads up.
Okay.
But I got a question from Melanie James that asked if we are going to discuss a composite function, limits of a composite function. Maybe Tom, you could put that in the back of your mind. He's ready to go. Things to watch out for. I got a thumbs up from that. So Melanie, we are prepared here.
Tom is going to take a look at one of those. I think one of those questions was posted on the Facebook page, and I think Tom's going to take a look at that near the end. So we'll be ready for that. So this idea, this example, I think leads me to an intuitive definition or an intuitive idea of an infinite limit. So if we have a function that's defined on both sides of a, except possibly at a itself, this expression, this notation means that the values of f can be made arbitrarily large as we want, by taking x sufficiently close to a but not equal to a. And, you know, we've seen other notation for this on AP calculus exams. For example, we've seen something like this: f of x goes to infinity as x goes to a. And once again, I'm sorry, I don't mean to overemphasize this, but even though infinity, that symbol is not a number, we often read expressions like this: the limit of f as x approaches a is infinity. F of x becomes infinite as x approaches a. Or f of x increases without bound as x approaches a. So all very common. Now, as you might expect, there's a similar definition if the function is decreasing without bound. So I won't go through a numerical or a graphical example of that, a specific one, but here's the definition, the intuitive idea. If a function is defined on both sides of a except possibly at a, this expression, the limit as x goes to a of f of x equals minus infinity, means that f can be made arbitrarily large in absolute value, or a way that I like to think of this, arbitrarily large negative, by taking x sufficiently close to a but not equal to a. I'm going to add in just a little bit here as an aside. We don't need to do this in AP calculus. But I remember, at least in my calculus class in college, we used to think about the epsilon delta arguments and the m's and the n's in cases like this. So you might think about just a very strict definition about what that means. That's a nice exercise for your really good AP calculus students. So how do we read this type of limit? This type of expression? This is the limit of f of x as x approaches a, and it is negative infinity. That means f decreases without bound as x approaches a. And here's an example of that. And you'll notice that I've sort of drawn in here an extra dashed vertical line, and I'll get to that strict definition in a minute. That's where a lot of this is leading, as you might expect. Here, as we approach a from both sides, the value of the function is decreasing without bound. Beautiful. We're getting there. We're getting to an example, and there are certainly similar definitions involving one-sided limits. Again, I won't do a numerical example, but here are some graphs to justify some of this. So I'll just take a quick look at a couple of these. This one over here in the top left-hand corner is an example. As x goes to a from the left-hand side, f of x is approaching infinity. It is increasing without bound. And let's take a look at this one down on the bottom right. As x approaches a from the right-hand side, the value of the function is decreasing without bound. So, okay, I believe that all of those limit definitions, all of those intuitive ideas of a limit lead to the definition of a vertical asymptote. I often get this question, well, what is the definition of a vertical asymptote? And this is it in my opinion. So this line x equal a is called the vertical asymptote on the graph of y equal f of x if at least one of the following limit statements is true. So I'll get this question frequently. How do I decide whether or not f has a vertical asymptote at a particular value a? Well, I've got to show that at least one of these limits is true. So there's a couple of two-sided limits in here, and over here on the right-hand side, these are one-sided limits. If any one of them is true, then there's a vertical asymptote at x equal a, usually drawn with a dashed line. Well, I thought this might be a good place to ask a question or two here, Curtis. Maybe we can get an answer. I'd like you to take a look at this, this example too, and I call this an asymptote with a hole. It's really a graph with a hole, I suppose. So I've drawn this function, y equal f of x, a graph of this function, and I've drawn it with a vertical asymptote at 1. It has an open hole at x equal 1. And the question is this really true? Is it really true in this case that the function f has a vertical asymptote? Is that definition above this satisfied? So is it really true here that this graph has a vertical asymptote at x equal 1, given the way that I've drawn it? And then I'm going to ask a follow-up question to that. Any answers to that at all, Allison? Anything coming in, Curtis? Is that true? Does that graph really have a vertical asymptote at x equal 1? The way that I've drawn it.
So the way that you've drawn it, it looks to me like I'm going to answer it. I'm waiting for something to come across in the chat, but I'm going to stick my neck out here. Steve, forgive me. I didn't do my homework.
Okay.
I apologize. But you told me just up above that at least one of those, any one of those had to be true, right?
Right.
And it appears that I do have a left hand, if I come in from the left, that I am approaching, I'm getting larger and larger without bound, right?
Right.
So I think that you can say, or that the idea that there is a vertical asymptote at a.
Absolutely, I believe there's a vertical asymptote here at x equal 1. Absolutely. So let me extend
and now
this.
I've got a couple here. I would call it one-sided graph with an asymptote. Scott Berger says this. Renee Williams says, given the definition above, yes, vertical asymptote at x.
Very good. Very good.
Kim
So let me add one more.
assumptions.
Let me add one more thing, and then maybe we'll draw a conclusion here, Curtis. What if I change this graph just a little bit here and I color in that hole? So the graph, pardon me, the function is actually defined at x equal 1. Does it have a vertical asymptote at x equal 1 now?
I'm going to let the people on the chat answer that question. I'm not going to try, but I am going to ask the question that Scott Berger did come up with while we're waiting for the answers to come in. He asked if it oscillates horribly without bounds, such as g of x is 1 over sine x, 1 over x times sine 1 over x. We should avoid calling it a vertical asymptote.
We should avoid calling what, x equals 0 a vertical asymptote?
I guess x equals 0, yeah.
Yeah, well, I believe in that case that graph does not go off to plus or minus infinity.
Right.
So there is no vertical asymptote there. It oscillates infinitely often back and forth between 1 and minus 1. Yep. But I don't think I would call that, by the definition, I wouldn't call that at x equals 0 vertical asymptote. Yeah.
Perfect.
Hey, Steve.
So we do have some answers. Everybody's still saying yes. The left-hand side still tends to infinity.
I agree. Go ahead, Tom. I'm sorry. Very good.
The example Scott came up with is actually the sine of 1 over x times 1 over x. So as x approaches 0, not only is it oscillating.
He had. I thought he had x
going off the charts too.
Okay, so what does he have? This one, Tom, or this?
Yes. No, it's
first one. The first one.
Okay, yeah. So in the first one, as x approaches 0 from either side, then the first part of that is increasing without bound. Okay, times.
Right.
Yeah. Okay, so I can see where there could be a vertical asymptote there. Yes. Okay. Okay,
yeah.
So back to this one. Over here, I agree that there is indeed a vertical asymptote, and I guess the point that I'm trying to drive across here is that as long as one of these limits is true, we do have a vertical asymptote. But I also want to emphasize that for a vertical asymptote, the graph of the function cannot cross that vertical asymptote. So we can have something like this. This function is certainly discontinuous, but the graph cannot cross that vertical asymptote.
Okay.
Very good.
But it can be defined at the vertical asymptote.
But it could be defined there.
Yeah.
Very good. All right, I'm going to take a look at one more example, Curtis, if it's okay. I'm going to try to take a look at these two one-sided limits, and I'm going to try to solve this analytically. I'm going to take a look at the graph, which will suggest some answers, but then I'm going to try to solve this. I'll show you a way that I would do this analytically anyway. So here's a graph of 3x divided by x minus 1, and it sure looks that as we approach 1 from the right-hand side, this graph is going off to plus infinity, and as we approach from the left-hand side, the graph is going off to minus infinity. So remember, the graphs sometimes lie a little bit. We want to see if we can show this analytically, but that gives us a good idea of what's going on. So here's how I might solve this or show this analytically. So 1 is not in the domain of the function. But if x equals 1, the numerator is equal to 3, which is non-zero. The denominator is 0. So that's a sign to me that I need to do something. I can't just draw a conclusion right away. I need to do something. And I'm going to take a look at these two one-sided limits. So as x approaches 1 from the left-hand side, let's see. So I'm approaching 1 from the left-hand side. The numerator is going to 3. And at least the way that I do this in my class, the denominator is approaching 0, but it's approaching 0 through small negative values. And that's the way that I would denote that. I know and I understand that some people are uncomfortable with the equal sign here, but this is the way that I do it. This is my notation. I'll take ownership for that. So the way that I see this is that the numerator is approaching a constant positive value 3. The denominator is getting smaller and smaller negative. And I can reason now that that's driving the whole fraction to negative infinity, decreasing without bound. Similarly, as x approaches 1 from the right-hand side, again, the numerator is going to 3. The denominator this time is going to 0 through small positive values. So that's driving the whole fraction larger, increasing without bound, going to plus infinity. And that certainly begs this question, I think. How do you write this? The limit now as x goes to 1 of 3x divided by x minus 1. What do you write here? Well, if this were the only problem given, if I asked my students to investigate that, I would hope that they would take a look at the two one-sided limits. Since the behavior on the left is different from the behavior on the right, this one has got to be a do not exist. So that's a doesn't exist, and I don't have any special notation to describe that behavior. The two behavior on either side is different. So I like that one. Okay?
Yep. I do have one quick question, Steve. It's not necessarily related to the math there, and that is the graphs that you're generated. What are you using? What's the software you're using to generate those?
I use Mathematica to generate most of my graphs.
That's what I thought. Okay.
All right. Now, these are exercises that are not in the problem of the week, but these are some exercises for you to think about, given what we've talked about. You should investigate or find the vertical asymptotes of the graph y equal log x. There seems to me that on almost every AP calculus exam, traditional one, not counting 2020, somehow the log of x is in there in some sort of a limit as x approaches 0. Sometimes there's a different argument in there, so it's good to know about the function, the log, natural log of x. You should think about the vertical asymptotes of the graph y equal to tangent of x. You should be able to identify those. And here's kind of a nice one, I think. You might think about using technology to sketch this graph and find the value of each of these limits. A couple of one-sided limits and an overall, what I would call an overall limit. And you will see that there is an issue here at x equals 0 because plugging in an x equals 0 gives me an x equals 0 in the denominator there. And so we've got to investigate this analytically, graphically, numerically, maybe to figure out those limits. So I like those as sort of a culmination of what we've talked about.
Steve?
Yes.
Quick question that just came in, and that is, if both of the one-sided limits go to, say, positive infinity, we should not say that the limit does not exist, right? Should we say that it does just approach positive infinity?
So
supposing that we have...
If this is true, and this is true, so the behavior on the left and the right is the same, then it's certainly okay to write this.
Perfect.
Okay, in some sense.
And would it be, and it would be incorrect to say DNE?
Well, I don't know about an AP. I don't know about an AP exam. This is a special case. This is special behavior where a limit does not exist. So if you said to me, the limit doesn't exist, is that technically correct? Yes, but this particular limit has special behavior that I can describe.
Okay, so you're not sure what the expectation might be.
Tom, how would you answer that one?
Well, yeah, I think DNE is still appropriate. What Steve's done here has gone further and been really explicit of what the behavior is like that's leading to the does not exist. In terms of AP, one thing you would just never see is a multiple choice question where both DNE and plus or minus infinity were choices.
Agreed.
They would never put you in that situation because the plus or minus infinity, they're descriptions of behavior. They're not numbers.
Not numbers. Yep.
Sounds like we've got Julie Marshall has weighed in here and said that AP will take either one, infinity or DNE.
I think that's true on a free
response question, yeah.
And I don't think they would give those as competing options on a multiple choice.
I agree. All right, well, let's switch gears just a little bit and let's take a look at limits and infinity, Curtis.
That sounds awesome.
So this is the second half. Limits and infinity.
Let's take a half. We didn't even have a halftime show.
Let's take a look at some limits in which x increases or decreases without bound. And I'm going to start out in the same way. I'm going to try to discover what's going on by taking a look at a particular limit, a particular function, and I'm going to explore this numerically and graphically. So this is one of my favorites, 1 divided by x squared plus 1. And I'm going to look at this as x increases or decreases without bound. I apologize. I've kind of made my table a little bit more compact maybe than I should have, but there's an awful lot of symmetry in this function also. So in the first column here, in the x column, I've listed plus or minus values of x because there's an x squared in here. And I've got the value of the function in here, and you can see that even as I get close to 500, the value of the function is very, very close to 0. The graph on the right-hand side tends to back that up. Even as I get close to 4 or 5, I'm pretty darn close to the x-axis. And so this sort of suggests, this table and the graph suggest that as x increases without bound, the value of the function approaches 0. So that line y equals 0 we call a horizontal asymptote. And it appears that we can make values of f of x as close to 0 as we want by taking x sufficiently large. And again, this is kind of an intuitive idea of this limit, but you might think about a more formal definition. Here's the notation that we use. The limit as x goes to infinity of 1 divided by x squared plus 1 is equal to 0. Again, we recognize that infinity is not a number, but rather a symbol. But this is describing the behavior of this function as x increases without bound. So if f is a function defined on some interval a to infinity, then this limit expression means that we can make f arbitrarily close to L by taking x sufficiently large. And I'm going to do the same thing here, Curtis, if it's okay with you. I'm going to take a closer look at this, draw a couple of pictures here. Here's some other notation to be sort of similar to what we talked about before. Sometimes we see this. F of x goes to L as x goes to infinity. And again, even though that is a symbol and not a number, we often write things like this. The limit of f of x as x approaches infinity is L. And there's a couple of other phrases for you. Here are some possible graphs, and I drew these because I wanted to emphasize that a graph of a function can indeed cross its horizontal asymptote, in fact, infinitely many times. That can't happen with a vertical, but the graph can cross a horizontal asymptote, especially take a look at this one on the right-hand side, where it tends to sort of oscillate but zero in on that value y equal L. Well, okay, of course, there's an intuitive idea of a limit at negative infinity, the limit as x goes to minus infinity of f of x equals L. I think you sort of get that. And here's the definition of a horizontal asymptote. So the line y equal L is a horizontal asymptote of the graph of y equal f of x if either one of those two limits is true. And I'm going to add a little bit more down at the bottom here. I want to add in the limit as x goes to infinity of f of x equals L1, and the limit as x goes to minus infinity of f of x equals L2. So the question is, if those two limits are true, does L1 have to equal L2? Or maybe another way to say it, can L1 and L2 be different? So maybe you could throw that question out there. We'll get an answer here, and then maybe I can try one more example anyway. Do those two limits have to be the same?
Well, I would think that they wouldn't have to be, but
more confidence, Curtis, more confidence.
Well, I'm trying to draw a picture in my head of a graph that might make that, like cotangent, I guess. Is that
yeah,
right?
can you think of a quick one where this is true?
What, arctan?
Very good. Excellent, Curtis. Sure, very good.
No, I can't take credit for that. Scott Berger put that one in the chat.
Very good.
That was what I was thinking, though, when I said cotangent.
Quick recovery.
I was trying to do the inverse of tangent.
Yeah, so those two values, L1 and L2, do not have to be the same. So it is possible for the graph of a function to have two different horizontal asymptotes. Can't have more than two, but it could have two different ones. Okay, now if you're teaching this, if you're about at this place in the syllabus, I want to remind you that you probably haven't done anything with L'Hopital's rule yet. And so there are still some good analytical techniques here to find some of these limits. And you know what? They are very useful procedures because I think I see students using some of these, some BC students using some of these procedures when they get to infinite series. So don't lose sight of these. Suppose I want to find the limit as x goes to infinity of this rational function. So the traditional way analytically to find this is to divide both the top and the bottom by the highest power of x in the denominator. So you know that the AP Calculus curriculum is stressing communication and notation. So I just want to point out that I have not executed that limit yet. So I'm carrying that along. So I divide the top and the bottom by x squared. I carry through that x squared. I write this as separate fractions here. And there's a lot going on now between here and here. The limit of a quotient is the quotient of the limits, provided that the limits exist. And I want to use the word distribute, but I'm going to take the limit of a sum as the sum of the limits. Eventually, I can take the limit of each one of these terms here, and I'll get a 2/5. So that's a very common analytical way to find a limit of a rational function. And I guess I would suggest don't let your students lose sight of this process. I think it's a very important one. So here's a couple of notes with a couple of exercises maybe, or a couple of things that you can try. You might think about, if we have a rational function, can you come up with some sort of general answer to this or general way to find this limit? If you have any rational function, I think that's a good exercise. That's a good project for some of your AP Calc students. And here's a nice problem to work on. Can you find both the horizontal and the vertical asymptotes, if there are any, on the graph of this function? So that's a nice one. I think you should take a look at that. And don't forget that there are these other limits in infinity. I'm not going to talk about these, but there are these other limits. For example, the limit as x goes to minus infinity is minus infinity. What does that mean? As x decreases without bound, let's see, so does the function. The values of the function decrease without bound, become arbitrarily large, negative.
So Steve, on your first question there, I've got a comment from Jason Kang, and I actually was thinking the same thing. So Jason, I'm going to ask your question for us. It says, can we use the rules for finding horizontal asymptotes by looking at the leading coefficients since the powers are the same? I was kind of thinking the same thing, that, you know, if we've got a rational function and we can kind of explore the fact that the denominator and numerators had the same power, same right?
Degree. Yep.
They were the same. So couldn't we just look at the leading coefficients?
Absolutely. If you have solved one of the parts there, one of the cases, and that is where the degree in the numerator is the same as the degree in the denominator.
Right.
So that's excellent. So now there are two other cases where the degree
right.
in the numerator is less than the degree of the denominator. What if the degree
the denominator would increase faster than the numerator, and we'd get a 0 or whatever our plus c is, and then the opposite being the case of the numerator, right?
So what is the degree in the denominator? Yeah,
that's a great way to look at those.
Yep.
Good comment, Jason.
Yep, you look at the degree of both the numerator and the denominator. Excellent. All right, I'm almost ready to.
We're talking about. Sorry, Steve.
That's
we're
right.
talking about end behavior of the functions. Effectively, is what we're talking about when we're talking about limits at infinity. That's a question more than a comment from Samuel.
All right, let's see. I'm going to try this. Is that still visible, Curtis? Is that okay?
Yeah, looks great.
Okay, let me see if I can expand that just a little bit. There we go. So these were our 914 questions that have to do with limits at infinity and infinite limits. And I'm going to take a quick look at these, and then I'm going to turn it over to Tom to do a little bit with technology. So I presented a couple of graphs here, a graph of y equal f of x, a y equal g of x. And I asked participants to use the graph of f and the graph of g, I guess, to evaluate each of these limits, and if they don't exist, explain why. So let's see, I don't know if I can get all of this on the screen at once, but let's see what we can do. The limit as x goes to -2 of f of x. I'm going to sneak in a little equal sign there. Well, let's see, there's -2. F of x is on the left-hand side. As x approaches -2 from the left-hand side, the value of the function is increasing without bound. So that's a plus infinity. So I've actually drawn in the horizontal and the vertical asymptotes on these graphs, so there will be no issue here. It's kind of hard to see, but both of these graphs do indeed have horizontal asymptotes at y equals 0. As x approaches -2 from the right-hand side, well, let's see, I'm going to -2 from the right. The value of the function is going down here, decreasing without bound, so that's minus infinity. And so now what happens is we take a look at an overall limit. Well, the behavior on the left is different from the behavior on the right. So I'm going to have to write in here DNE, does not exist. The limit as x goes to 2 from the left-hand side, let's see, of f of x. Well, real quickly, as we approach 2 from the left, this is going to plus infinity. As we approach 2 from the right, it's also going to plus infinity. And therefore, the behavior on the left and the right is the same. So we can put a plus infinity over there. And I understand that graphs lie a little bit here, but the limit as x goes to 0 of f of x, you can see that this crosses at the origin, so that's equal to 0. That's not a limit at infinity or an infinite limit, but I put that one in there anyway. And as x goes to infinity here, as x increases without bound, the value of the function is getting closer and closer to 0. I kind of like that kind of a problem. We use a graph here to get an idea, or to use the definitions of limits. I like that. Let's take a look at another one here that's dependent upon the graph of g. We're going to use the graph of g to evaluate each of these limits. As x goes to minus infinity, let's see, so x is decreasing without bound. If I've drawn everything correctly, it sure looks like that function is approaching -3. I've got a horizontal asymptote in there. And here, Curtis is an example of a graph that has two different horizontal asymptotes. So it's, whoops, I'm sorry about that. As x approaches infinity, the value of g is approaching 0. And as x approaches 0, I just put that in there for the heck of it. G of x is also approaching 0.
Yep.
So here is the third one I think is nice, because now we're combining the two graphs. I think I've got the third one in here. There it is. So let's see if we can answer any of these at all. And Tom, help me here. Don't let me make a mistake on any of these. As x goes to 2 from the right-hand side, what's happening to this quotient? Well, let's see. As x approaches 2, and I'm just going to scribble a little bit. I'm not suggesting that any of this notation is valid, but as x approaches 2 from the right-hand side, the function f is increasing without bound. G, what's G approaching? Well, G is approaching some constant value, I don't know, around there. I'm just going to say it's 1. It's around 1, but it's a positive constant. So here's how I'm going to argue. The numerator is increasing without bound. The denominator is approaching a positive constant close to 1. And so that limit, I believe, from the graphs is infinity. What if we look at this the other way? G of x divided by f of x. Well, this time g is approaching some constant, let's see, from the left-hand side. Again, it's around 1. Maybe it's a little bit bigger than 1. I'll put in a 1.5 for the heck of it. And what happens to f as x approaches 2 from the left? Let's see, as x approaches 2 from the left, f once again is increasing without bound. And so here's how I would argue. The numerator is approaching a positive constant. The denominator is getting larger and larger. That drives that whole fraction to 0. How about that?
Like it.
Now, C is a cool one, I think. The limit as x approaches -2 of g divided by f. Let's see. As g approaches pardon me, as x approaches -2. Well, I'm going to skip ahead a little bit here. I'm telling you, I've looked at this a little bit, and I'm going to have to examine this with two one-sided limits. So I'm going to take a look at the limit as x approaches -2 from the right of g of x divided by f of x. I'm going to take a look at the limit as x approaches -2 from the left of g of x divided by f of x. Tom, watch me on this one. Don't let me make a mistake. As x approaches -2 from the left-hand side, let's see. What's g approaching? Well, let's see. G is approaching, well, okay, right around there. Let's say -2. How about that? As x approaches -2 from the right, let's see, what's f doing? F is going to -infinity. So here's how I see the behavior there. The numerator is going to a negative constant, a constant. The denominator is decreasing without bound. So that drives the whole fraction, I believe, to 0. As x approaches -2 from the left-hand side, I believe the numerator here is still going to -2. The denominator, however, this time as we approach -2 from the left-hand side, f is going off to +infinity. So the numerator, once again, is going to a fixed constant. The denominator is increasing without bound, and that drives the whole fraction to 0. So by taking a look at those two one-sided limits, they are the same. So I think it's okay for me to write up there that that's equal to 0. How about that? Let's take a quick look at D. I'm going to see if I can, whoops, I'm sorry. I'm going to see if I can sneak that in here. This is the limit as x goes to infinity of f of x plus the limit as x goes to infinity of g of x. I can split this up if both of those limits exist, and indeed they do. The limit as x goes to infinity of f is 0. The limit of as x goes to infinity of g is 0. So this one's pretty easy. That one's 0. Hey, and what about this one in E? This is a good one. The limit as x goes to 0 of f of x divided by g of x. Let's see here. Can I see my graphs a little bit? Oh, well, wait a minute. F is going to 0 and g is also going to 0. I don't have enough information in this problem to get an answer here. F is going to 0 and g is going to 0. This is a nice problem here where I can step back and say something like, you know what? I need another way to evaluate this limit. I need either some analytical expressions for f and g, or in a couple of weeks or a month or so, we'll get another way to evaluate this type of a limit. And finally, how about this one? The limit as x goes to infinity of f times g. I'm just going to put in 3 dots because I need to hand it over to Tom. Both of those limits exist. So this is the limit of f times the limit of g. And so this is just 0 times 0, which is also 0. So I think those are some good exercises which emphasize what we've talked about, what I've talked about tonight. And I also like this E over here because that leads us into something that we'll be talking about later on in the semester. And Tom, I think I'm going to turn it over to you for a little technology. Is that okay?
Sounds good.
All right, here you go.
That's great. As we transition over to Tom, I just want to point out real quick, we put the link to the materials that Steve was working with there in the chat. And you'll find the solutions there on Friday and the problems for next time up there ready to go on Friday as well. So those will be downloaded, and then we'll have our next meeting, I guess, 2 weeks from now on the 28th, ready to go.
All right. Give me some feedback, Curtis. Can you see my screen all right? The TI-Nspire.
Got you, man. I can see it.
Okay, great. So a couple things. Thanks again, Steve, for a great presentation on the limits at infinity and infinite limits. with regards to using the technology, I wanted to point out a couple of tips for looking at such limits, especially limits at infinity. I think sometimes people scratch their heads a bit about how one might use technology to explore such limits. And the hang-up, I think, is, well, if x is growing without bound, either x approaching negative infinity or positive infinity, that means I'm going to be dealing with a graphing window that's huge horizontally. And how would I deal with that? So I'm going to use an example here. I think somebody talked about arctangent of x. And I've got, oh, you know what? I think I'm in degree mode. There we go. Put in gradients. Okay. So what one could do is try to zoom out on such a graph. I'm on the Nspire here. So one way we could zoom out is, let's see, that's zooming out in both directions. So let me go to my window. And I'm going to set my x min to negative 10,000. And I'll set my x max to 10,000. Then I'll go ahead and make my, I'll just make my y min, y max, say negative 3 to 3. And let's take a look at that, all right? And this is the kind of behavior you could expect to see if you've got some limits at positive infinity or negative infinity, is you're going to have the appearance of a graph that looks like a horizontal line. And in fact, basically the graph is starting to look like the asymptotes. And this is an example of a graph with two horizontal asymptotes. If we were to turn on the trace, you can see that the y values are kind of staying steady around 1.57. That's kind of a notoriously suspicious decimal number that's approximating pi over 2. If we go to the negative side, see that negative 1.57. I just wanted to point out, let me go ahead and change my zoom back to kind of a regular, whoops, let's see, I didn't mean to do that. Let's try that again. There we go, there's our standard.
Hey, Tom,
yes.
do me a quick favor. You can actually hold down the shift key and grab that horizontal axis, and you can do that zoom without having to go to the window.
Yes, that's what I forgot to do. Okay.
You can hold down the shift key when you grab that.
Hold down the shift key, grab one of those.
There you go.
Keeping the vertical.
Keeping your verticals the same and zooming on there.
Dimensions are staying constant, but I'm able to zoom out horizontally that way. So yes, that's a nice way to do that. Did want to point out another technique that people can use, and that is that if you want to explore limits at infinity, one way to do it would be to replace x by 1 over x, and then look at the behavior as x approaches 0 from the right and left. The idea being 1 over x is going to be growing without bound toward positive infinity as x approaches 0 from the right. Simultaneously, as x approaches 0 from the left, 1 over x will approach negative infinity. And so you can get a feel for what the behavior is like by just doing that simple composition and then turning your attention to x equals 0. And that's a pretty nice way to think about it. So I'm going to go ahead and do that here. what I'll do is I'll bring up I've got inverse tangent of x. I'm going to change the x to 1 over x. And again, the reminder is we're now going to be interested in what's the behavior near 0. Okay? And now we can see this kind of jump, this continuity. And remember that this is suggesting the limiting behavior of the arctangent of the argument as x of the argument as it increases without bound. Okay. And here what I'd want to do is actually zoom out. So I'll take Curtis's Q and pull that out. And we can see that behavior again.
So Tom, it appears we do have numerical values that we can tie the answer to that to as x approaches negative infinity and positive infinity. Is that correct?
You mean exact values? Like
it looks like we have exact values that we can tie this to. Can you confirm those?
Confirm and let's see. Depends on what you mean by confirm.
I've got a question that's here from Samuel. It looks like these should be pi over 2 and negative pi over 2.
Absolutely, that is correct.
That appears to be exactly correct. But
exactly correct.
I wasn't
doing
a very good job of leading you there. I apologize.
Really, just the technological exploration. Yeah. So, okay. Anyways, that's a simple. I wouldn't call it a trick. It's just it's a strategy one can use to explore limits, and that's the verb I use when I'm using technology around the topic of limits is exploration and investigation. Those are the verbs I use rather than proof. Okay, I would never say that a computer-generated table or graph would provide a proof. Now now if one happens to have a computer algebra system, that might be a different story. But this is we're just looking at graphical and tabular explorations.
Well, that's a very shrewd what you just did there using 1 over x. That's a really nice bit of understanding, and I think that's a good.
Turned out to be a pretty robust way to do
just shrewd understanding. I like that.
Tom, I'm always amazed at what the TI-Nspire can do as a computer algebra system. I apologize if you're going to do this, but you can actually ask the machine to evaluate this limit, right? As x goes to infinity.
Yeah, and I happen to have a
which is very cool.
CAS on this one, so I'll go ahead and show that quickly. Let's see. Yeah, let's bring up the limit. And if we wanted to look at the limit as x approaches infinity, let's see. Cheat here a little bit. There's my infinity symbol. Whoops. Get over here.
And that's
we could put in our tangent of x here.
Oh, sure. Okay.
And we get that limit of pi over 2.
Very cool.
So, with the time that we have, I thought we might address, I think a question came up about composition of functions arising in limits. And I think this was an example that came up. Mark Rowley pointed this out to Steve Kokoska, and so I thought I'd take a look at this. And this was a problem, I think, that caused quite a bit of discussion. I've got some functions entered here that satisfy these properties. Limit as x approaches 9 of f of x is equal to 6. The limit as x approaches 6 of f of x is 9. And f of 9 is actually equal to 6. So I guess from that, we could actually conclude that f's continuous at x equal 9. Now the limit as x approaches 9 of g of x is equal to 3. The limit as x approaches 6 of g of x is equal to 3, but g of 6 is actually equal to 9. So it looks like g is not continuous at x equal 9. And then the question is, what's the limit as x approaches 9 of g of f of x? Okay. Well, I'll let you think about that a little bit. And what you might be thinking, well, is as x approaches 9, f of x is approaching 6. And if that's approaching 6, then g of f of x should be approaching 3. Well, let's check it out. 3. Is that really, let's see, is that what we expected to see?
So I'm not sure. Walk me back through. Okay, there's my definitions again. Okay.
But does that really show up graphically? Let's take a look. Here's the graphs of f and g. G is actually equal to
3. Okay.
9 at 6.
Okay.
So I'm going to look at this graphically and see, does that limit actually make sense? So I'm going to actually plot g of f of x.
That's good.
And let's see. So as x approaches 9, this is actually up at 9. So that limit is actually 9. And the issue
do me a favor,
is,
can you trace that? Use
Sure.
the trace, like trace all or something, and type in 6 so we can see. So we can see that value. Can you arrow over to, there you go, over to 6 there? Okay, perfect.
oh, excuse me, I want to be at 9.
Okay.
Is that showing up all right?
Tom, can you go back to 2.2 for a second?
Sure.
Oh, go back one more. I apologize.
So this is not really what the graph is showing to us.
Where's F?
Yeah, this really should be 9.
Well, that's interesting.
And,
Yeah.
So
and
what's
the
going
reason
on here,
is
Tom?
that as
Walk
X-
us through it.
Okay, so walking us through as x approaches 9, well, let's look at these actual definitions. As x approaches 9, f of x is always 6, right?
Yep.
As soon as you get past 7, it's a constant 6.
Right?
That means g of f of x is 9 over an entire interval around.
Oh, yep. Okay. Sure.
Did I mess this up?
Nope. I think
Maybe
we're
this was
there.
what I'm supposed to look at.
Yeah.
No, approaches 9.
As
So
X
g of
approaches
9.
9. Oh, this is a good one.
This is a good example.
Yeah.
Mm-hmm.
So even though there's only one value where g is equal to 9, it turns out to be the limit of this thing. But it's for this particular setup. So these are
Right.
very subtle. Very subtle
Can you
limits.
show us the graph again?
Sure, absolutely.
So I'm not sure that okay. F of 3. It's 9. Because when, okay. Yeah. Okay.
I
Yeah,
don't
that's
know how
a good
clear this.
example.
It's a very subtle example, and it's owing to the discontinuity in G that you have to be very careful with these compositions of functions.
So
'Cause I think
got
looking at
another
this,
composition there drummed up. I know we had a question early on
get
about
rid of
what
it.
things to be cautious of. I know that we have a question about some of the things to be cautious of, and in here you're showing us that we really need to be cautious about the domain of our functions, right? That what we're to be extremely careful with where things are defined and how they're defined, and how that might affect the composite function.
So Tom, your example is one in which, you didn't get what you expected as you reasoned out. However, I guess I have two questions. Maybe we could leave these for our participants. I think that one of them is, I'm guessing that I could come up with another example that would have a different limit that fits these 6 or so conditions, but I might have a little bit different answer.
Yeah, and I think we can go ahead and do that right here. I'm going to change the definition of F slightly. Go back to page 2.1. Nothing has changed.
Okay.
Everything is the same.
Mm-hmm.
And now we have a very different look here.
Right. And so I think a question that maybe we could leave open is,
notice this limit is 3 now as x approaches 9.
And so
Scott Berger just brought that up, Tom, as a matter of fact.
How do we know when that limit exists? How do we know when we can reason that out and get an answer?
Yeah.
What are the conditions necessary?
So continuity of G would have been 1.
Right. Yep.
And what we've illustrated here is fitting those conditions. I've come up with examples where the composition's limit was 3.
Yep.
And then one that fit all the same conditions, but the limit of the composition was 9.
Right.
And so that means there's not enough information to determine the limit.
Yep, I agree.
Great, and I think problem. We've got some folks here putting that in the chat, talking about this. So Scott Berger said it depends on the choice of F and G.
Right.
And he went straight to your x minus 3 example for f of x.
Oh, wow.
And that changes things. And then because f of x is continuous, you can bring in the limit. That was what Melanie was talking about there. So we've got a few people chatting about this as well. So this is really a good and an interesting example. Certainly enjoyed seeing that.
Yeah, and our thanks to Mark Corrali for bringing this to our attention. He said it was a kind of a hot topic recently.
Yeah.
Discussion boards, and so we thought we'd take a look at it.
Yep. Well, guys, this was really good. Tom, unless you have anything else,
I'll stop sharing and turn it back over to you.
I think we can kind of wrap things up. So really, really appreciative to the two of you guys sharing your expertise and giving your time to do this. Oh, we had one more comment there. Samuel says, as long as the limit of the inner function exists. And so I think we can move on from there, right? So as long as the inner function exists, then we can kind of work on
well, the function G, I think Tom pointed out, has to be continuous also at that limit L. At that limit.
Yep. Mm-hmm. Mm-hmm. Right. Yeah, so anyway, I really appreciate you guys sharing your time and expertise. Certainly enjoy this. I always learn a little bit of calculus, it's good to get back and scratch a little of the rust off. I promise I'll work my homework for next week or for 2 weeks from now. So thanks you guys very much. And to everybody in the audience, you guys be looking for the solutions on Friday at that link that we've posted in the chat. And then the new problems for September 28th will be starting at the same time, same place. Look forward to seeing you guys then. So thank you very much and have a good evening.
Thanks, Curtis. I hope people will send in their questions. That would make it even more enjoyable. Thanks, Curtis.
Yes, it certainly will.
Thanks, Tom.